All right. While we were away, the little Fisher-Price guy said, "Hey, Watson, let's look a little bit more at these E2 reactions. I want to find out a little more information on those." All right, Fisher-Price guy, let's take a look. So, we'll start with the stereochemistry of E2. Note, when we're looking at the transition state of the E2 mechanism, we had some issues here. If we go back a couple pages, we see in the transition state that everything is happening at once. The base is attacking, the beta carbon's hydrogen, double bonds forming, the leaving group is leaving. And recall, bromine, our good leaving groups, are usually pretty big. So what's going to be the best orientation of the molecule for the base to come in and take that hydrogen so as A, not to get in the way of the bromine leaving, and B, it turns out when we have to form the double bond, there's only two orientations that are going to work because this bonding pair of electrons here must form a pi bond between these two carbons. Right now, those electrons are overlapping with the hydrogen's electron with the carbon's sp3 hybrid orbital. That sp3 hybrid orbital must change into an unhybridized p orbital in order to get that pi bond to form. It turns out the only way that that's really going to happen is if this bond here, the carbon-hydrogen bond, is in the same plane as the carbon-bromine bond. Because as this bromine is leaving and taking the two electrons with it, this carbon also becomes sp2 hybridized and generates an unhybridized p orbital. And the deal is those two unhybridized p orbitals must be in the proper orientation. They must be lined up parallel to each other in order to form that pi bond. So the only way that's going to occur is if the hydrogen and the bromine are in the same plane, which means if the bromine is going down this way, the hydrogen can be going up that way. Or it turns out if the bromine is going down this way, the hydrogen could be also coming down the same direction. However, bromine's a big group. You got to get a base in there. So the best way for this to occur is if the bromine is going down this way and the hydrogen is going up that way. We have a name for that orientation. If we go back and look at these pages here, all right. If the hydrogen and the leaving group are in the same plane but on the same side, we call that syn-periplanar. They're eclipsed with each other. If they're in the anti-position, we call that antiperiplanar, and that is going to give us our lowest energy conformation. There's going to be less steric hindrance. And so in order to get an E2 elimination, the leaving group and the hydrogen must be in the antiperiplanar orientation. So, if we look up here, we see here's our molecule here. We've got two phenyl rings on the carbon containing the bromine. We note the bromine's going up this way. We have a hydrogen going back away from us and down. The phenyl group coming towards us and down. On the beta carbon, we've got the phenyl ring here, a CH3 going back, and this hydrogen is going up. Note, we're going to do an E2 elimination. Here's our alpha carbon. Here's beta. Yes, there is a beta carbon right here on the phenyl ring, but it does not have any hydrogens on it, so we're not going to get any elimination here. We can't get a double bond here. This hydrogen is not in play because it's not on a beta carbon. This is on the alpha carbon. So we have our strong base. It can only take this proton and make a double bond between these two carbons here. However, the way this is drawn, these are not antiperiplanar. These are synperiplanar. Good news, this is a carbon-carbon single bond, which can rotate. This bond will rotate. If this hydrogen is up, we can rotate it so that this bromine is going down. Note that that's a 180-degree rotation. The bromine's up this way. We want the bromine going straight down this way. 180-degree rotation means this phenyl group that is coming out towards us and down, after 180-degree carbon rotation of this bond, that phenyl group will be going away from us and up. So this phenyl group is will be going away from us and up. The one over here is going towards us and down. We can see this will lead to this isomer here, where the two phenyl groups are trans to each other. All right, so on exams, make sure to watch out for that. Make sure that when you're doing your E2 eliminations, when you see the stereochemistry here, make sure you rotate that carbon-carbon double bond or single bond such that the leaving group and the beta carbon's hydrogen are antiperiplanar to each other. And usually this isn't a problem because single bonds can rotate. However, things get a little bit more interesting when we look at our good old buddy cyclohexane again. So, recall cyclohexane, here's a chlorine on a cyclohexane ring. Note in this chair conformation, the chlorine is equatorial. Of course, we could also always ring flip it, and that chlorine will be axial. But here's the deal. For an E2 elimination, we need the chlorine and the beta hydrogen to be antiperiplanar to each other. This chlorine right here, is there any hydrogen that is antiperiplanar to it, that is on the beta carbon? Well, this hydrogen here is about the same orientation. Note, this one is not anti to the chlorine. This hydrogen over here is like 90 degrees off in this drawing. It's not even with that chlorine. It's not anti. Which means this chlorine in this conformation of the cyclohexane ring with the chlorine equatorial, there are no hydrogens that are antiperiplanar. However, if you ring flip it, and yes, this is the higher energy state, but if you ring flip it and you put that chlorine axial, we now find out that this hydrogen that is beta to it is also axial. This chlorine's axial down, this hydrogen is now axial up. So you can get elimination. A base can come in and take this hydrogen, which is axial up, and the antiperiplanar chlorine that is axial down can leave as chloride. Take-home message for an E2 elimination: you need antiperiplanar arrangement. The leaving group and the hydrogen must be diaxial. The leaving group must be in the axial position, and you must have a hydrogen on the beta carbon also axial, because then it'll be in the opposite direction. So, what happens then if we look at this cis methylchlorocyclohexane versus the trans 1,2-methylchlorocyclohexane? Well, let's start with the cis, and note, if we want to figure out how to get things axial equatorial, we need to draw it in the chair conformation. So I drew it in the chair conformation here. I put the chlorine. So this carbon here that contains the chlorine is this one here. I have it going down, and the methyl is the next one over right here. Note the way I've drawn it, that is cis. If you draw a line down through the carbon-carbon bond, the CH3 and the chlorine are on the same, or excuse me, the line between these two carbons. The chlorine and the methyl group are on the same side, so it is cis. But our chlorine is equatorial, And as we said up here, it needs to be axial. No problem. We will ring flip it. Move this group up, move this carbon down, ring flip it. Recall all axial positions go equatorial, all equatorial go axial. So this equatorial chlorine becomes an axial chlorine, and this axial methyl becomes this equatorial methyl right here. And now we need to look, okay, are there any hydrogens antiperiplanar? Here is our chlorine axial up. On the next carbon over, going around the ring, do we have any hydrogens axial down? Well, yeah, here's this chlorine's axial up, this hydrogen's axial down on this side. A little tough to see, the hydrogen's axial down on that side, which means we can form a double bond between this carbon and this carbon on this side of the ring, and this carbon on that side of the ring. Note, we can form double bond. The chlorine will be gone between this carbon and this carbon containing the CH3. That's this one right here. A little tough to see looking at that, so it's always a good idea to then to redraw it in the cyclohexane shape, the hexagon shape. And we've got the alpha carbon was here. Here's the beta carbon where the hydrogen came from. We have this isomer. And we can form the double bond between this carbon that contained the leaving group and the beta carbon over here to get this isomer here. Note, di-substituted double bond here, tri-substituted double bond here. Good old Zaitsev says this is the major product. And that's if we start with the cis isomer. But what if we have the trans stereoisomer here? What if we have this guy? Well, we do the same analysis with our trans, and I've got my chlorine. I put him axial down already. Note if it's trans, I draw a line between the carbon containing the chlorine and the carbon containing the methyl. Note the chlorine is down here, the methyl is up here, so they are trans. And the chlorine is axial down. But note, on this carbon over here, the methyl is axial up. In order to get elimination, we'll need a hydrogen axial up here. We don't have that. Our hydrogen is equatorial. Now, if we ring flipped it, sure, we can ring flip this up, and then this equatorial hydrogen will become an axial hydrogen down, but then this chlorine will become equatorial. And recall, we need both the chlorine and the hydrogen to be diaxial. They both need to be axial. So, this isn't going to work. There's no hydrogen antiperiplanar to this chlorine when this chlorine's axial. Therefore, we cannot get a double bond between the alpha carbon and the beta carbon that contains the methyl. Note, this chlorine is axial down. On this back carbon here, we have a hydrogen that is axial up in the back there. So we can get a double bond here. We will only get this product. We will not form any double bonds here because we cannot get antiperiplanar. All right. So, next thing to look at real quick, E1 versus E2. When will the reaction run E1? When will the reaction go via the E2 mechanism? Well, both of them prefer tertiary alkyl halides. The main difference is E2 prefers strong base, hydroxide alkoxides. E1 prefers the weak bases, alcohols or water. So we really need to look at the base. But here's the deal. When you run an E2 mechanism or an E1 mechanism, whichever reaction you want to run, if you start with the same starting material, if your tertiary alkyl halide is the same, you're just deciding, well, I'm going to run this reaction, should I put in strong base and run E2 or weak base and run E1, you're going to get the same product. You're starting with the same substrate, you're doing elimination, you will get the same product either way. The issue is, though, that if you run it via the E1 mechanism, you're also going to get SN1 products too. Whereas if you use a strong base and run E2 mechanism, then you're only going to get the elimination product. So if you're deciding, oh, I need to do elimination, should I do E2 or E1? always try to do it E2. Always try to add the strong base, because then you don't have to worry about substitution products. All right. Let's see what we have on the next page. Well, Fisher-Price guy here is saying, as I am sure you are too, wait, elimination makes alkenes. Can't you also make alkynes? Why, yes you can. Now you have to run E2. You cannot run E1 very successfully to make alkynes. But if you start with either a vicinal dihalide or a geminal dihalide, vicinal dihalide, we have two halogens vicinal in the same vicinity. We have a carbon with a halogen on it, a good leaving group, and a hydrogen, and next door, the carbon next door also has a halogen and a hydrogen on it, a vicinal dihalide. Or you can have a geminal dihalide. Both halogens are on the same carbon, and the carbon next door has two hydrogens on it. Now, to get this elimination, we're going to have to do a double elimination. We're going to have to eliminate this hydrogen and this halogen here to form a double bond, and then this hydrogen and this halogen to form the triple bond. That's going to take a strong base. Two main ways to do it. First way is sodium amide, the NH2 minus anion. Very, very, very strong base. You would put in two equivalents of it, twice the amount, because you need one stoichiometric equivalent of amide to do the first elimination. The amide will take this hydrogen, and this halogen will leave. Then the second equivalent, the second amount of amide will take this hydrogen, and we'll get our triple bond. So two equivalents of sodium amide, or a little less harsh conditions, you can use our good friend potassium tert butoxide. Nice strong base, very sterically hindered, in DMSO, dimethyl sulfoxide, as our solvent. And yeah, that's how it works. Here's a little mechanism right here that we've gone through. Amide takes the first hydrogen, forms a double bond, leaving groups leaves to give us this alkene that still has a hydrogen and a chlorine, alpha and beta to each other. Another equivalent takes this hydrogen, chlorine leaves, and we've got our alkyne. So I think that's enough of E2 for now. In the next video, we will wrap up the chapter looking at, okay, SN1, SN2, E1, or E2, what gives?